Hi everyone, I'm Sai Srirampur and I'm here to talk about Postgres isn't slow, your storage is. In this talk, we'll double click on what are the common problems that Postgres users run into. We'll see that most of these common problems tie back to disk and IO performance. We'll also present the secret sauce to that solves most of these problems, which is local NVMe storage. We'll do a bunch of benchmarks which show local NVMe performance over EBS backed storage. And as an icing on the cake, we'll talk about how do we take this to production? How do we get an enterprise grade Postgres with local NVMe? Great to be here again. So let's dive right in. Postgres isn't slow, your storage is. Before I do that, I'll introduce myself. I'm Sai Srirampur. I lead all Postgres efforts at ClickHouse. Prior to ClickHouse, I was the co-founder and CEO of PeerDB, a Postgres replication company that was acquired by ClickHouse around 2 years ago. Before that, I worked on the Microsoft's Postgres team for about 5 years. And prior to that, I was an early engineer at Citus Data, which is the distributed Postgres database company. And by the way, this is my third time here at Posette. So very excited to be here, though this is my first time in the last 3 years. So it's great to be back. So let's get started. So, so the way I want to begin my talk is by highlighting 5 common problems that users run into with Postgres as their workloads grow. These usually show up once you are in that hundreds of gigabytes to terabytes range and when concurrency and throughput really start ramping up. Number one, you see that your ingestion pipelines slow down. This shows up a lot when the ingestion pipelines have updates and upserts. Jobs that used to finish in few seconds suddenly take minutes or even hours. Number two, read performance becomes inconsistent. Most queries are fine, but a few very important ones start getting slow. P95 goes from a few milliseconds to seconds, and sometimes even, queries timeout and your dashboards timeout, and there is bad user experience. Number three, vacuums can't keep up and bloat increases. As update and upsert throughput grows, table bloat increases, auto vacuum starts falling behind, and you could end up with gigabytes to terabytes of bloat. Number four, checkpoints also could get slower. Checkpoints start taking longer and could begin competing with your actual workload for resources. Number five, slow logical replication. We saw this often at PeerDB when customers were syncing their Postgres data to external systems like Kafka or ClickHouse via logical replication. These pipelines can degrade under load, wall decoding slows down, especially with large and interleaved transactions, and replication slot sizes begin to spike. One interesting observation, if you see, is all these 5 problems are related to disk. With slower ingestion, indexes no longer fit in memory, so more update and upsert operations require disk lookups. At the same time, increased wall generation begins to push against disk write limits. Number two, with inconsistent read performance, your working set no longer fits in memory, cache hit rates drop, more reads go to disk, and that's what drives up your P95 and P99. Number three, slow vacuums means more dead tuples. Cleaning those dead tuples means more disk reads and more wall generation. And it's the same story with checkpointing and logical application. With slow checkpoints, you have increased fsync and write load, often reflected in higher data file write and checkpoint sync wait events. And these two wait events are all IO related wait events. And with slow logical replication, your slot size increases, your decoding starts spilling to disk, and it's often related to IO reorder buffer write wait event, which is again a IO wait event. So if you see, all of these 5 problems are related to disk and IO performance. This slide shows the classic signs of a disk bottleneck, and you'll see that these patterns when you hit these kind of issues. On the left, IOPS hits the cap, demands keep rising, but the disk can't keep up. So Postgres can't push more work through. On the right, you see that the pressure shows up as latency spikes. Instead of stable performance, you get periodic stalls. This is where your P95 and P99 start to degrade. And at the bottom, you have queue depth, which continuously increases. Requests pile up because the disk can't service them fast enough. And backlog slows everything down. So the bottom line is that a lot of Postgres performance problems ultimately trace back to disk bottlenecks. Now, let's go through a quick thought experiment. What if disk wasn't the bottleneck? What if it behaved more like a second tier of memory? On the left-hand side, you see the standard memory hierarchy. First is CPU registers, where the latency is sub-nanoseconds. Next is CPU caches, where the latency is single-digit nanoseconds. You have DRAM, which is nothing but the buffer cache or shared buffers, where the latency is hundreds of nanoseconds. And the last one, the one that is blurred and that is the one which is in gray, is network attached SSDs. These are like EBS in the cloud, right? And the access for and the latency for disk access is in the orders of like milliseconds, right? It's somewhere between 1 to 10 milliseconds. Now, notice that gap. The jump from DRAM, which is shared buffers, to network attached storage, which is EBS, is 5 orders of magnitude. Every time Postgres misses the buffer cache, it falls into that gap, and that's the big reason for poor performance. If you see the yellow back box, right, that is local NVMe storage. So that is storage that is physically attached to your compute and does not need a network hop for access, right? If you see, it sits right in that gap and enables around 10 to 100 microseconds of latency for disk access. And that's roughly 100 times faster than EBS. It effectively behaves like a second tier of memory backing shared buffers. So what does that change in practice? For Postgres running on NVMe storage, cached misses are significantly less expensive. They return in microseconds instead of milliseconds. Wall fsync stop dominating commit latency. Commits become much faster and more consistent. And the third is vacuums become much predictable. Instead of being IO bound and spiky, vacuums become more CPU bound. So the key idea is that shrinking that latency gap through local NVMe storage fundamentally changes how Postgres behaves. Now that we understand why NVMe can solve the disk bottleneck with Postgres, can we let's try to answer the elephant in the room, which is, can we actually have this in production? Local NVMe is ephemeral in the cloud. So if the instance terminates, that is, it stops or there are hardware faults, the disk dies with it. So there are three worries. First is instance loss can cause data loss. Number two, NVMe doesn't support disk level snapshots, unlike EBS. So backups have to come from Postgres itself. And number three, disk capacity is fixed at launch. What if I want to scale up? I need to migrate to a bigger instance, and how do I do that? These are real, and I don't want to pretend that they aren't. But the question isn't whether local NVMe is a perfect drop-in replacement for EBS. The more practical question is, can we design around these limitations while still getting NVMe level latency with EBS-like resilience? And the spoiler is, yes, we can achieve that. But we'll come back to this question, which is the elephant in the room, in my part in the part two of my talk. So stay tuned. So far, I have said that NVMe can make Postgres really fast. To understand how fast, we ran a set of benchmarks on a few common Postgres operations, comparing Postgres on NVMe versus Postgres on EBS backed storage, which is network attached storage. In this part of the talk, which is the first part of my talk, we'll deep dive into those benchmarks. First, we'll talk about the setup across those benchmarks. Next, we'll analyze the results both with respect to latency and throughput. And last but not the least, the interesting part, we'll dig into what's happening under the hood using pgstat activity samples, eBPF based CPU sampling at the function level with Parka, flamegraphs, and more. The goal is to show why local NVMe can significantly improve Postgres performance and what's happening internally to drive those gains. Let's double click on the setup. We deployed 8 identical PostgreSQL clusters in AWS. Same instance family, same RAM and compute, same operating system. The only thing that changes is the storage type. Four of the clusters use NVMe backed instance storage, and 4 others use EBS backed storage with a 3K IOPS baseline. And this is the standard setup. We had multiple instances for each storage type, 4 of each, mainly to normalize variability across these benchmarks. All 8 clusters use the M6ID 4x large instance type, which is 16 vCPUs and 64 gigs of memory. And this also comes with NVMe backed storage, which is instance storage. PostgreSQL version is 18.3 and was built from source in release mode with symbols available. The dataset is PG bench, the standard benchmark with scale factor of 33,000. So there is close to 500 gigs of data, and which translates to 3.3 billion rows in the PG bench accounts table. And this is pretty representative of a fast growing, high scaling, PostgreSQL workload. For instrumentation, we used Parka, which is an open source continuous profiler for CPU and memory usage. There is Prometheus plus eBPF exporter for block layer IO latency. PG stat activity sampling at 1 hertz for wait events, and vacuum verbose with track IO timings for per IO per run IO timing. In future, we also plan to share all the code and full report on GitHub and make it available so that you're able to reproduce these benchmarks. So the workload that we'll be running is a 64 client OLTP update workload, 5 minutes per host, 16 threads under the covers, all 8 hosts firing in parallel. And the script is a simple PG bench, picks a random account ID between 1 to 3.3 billion rows and updates the matching rows and increments the balance. Let's analyze the results. So with all this benchmark, we saw that NVMe achieved 9x better throughput and latency than EBS. The median TPS, which is transactions per second on NVMe, across the group of 4 Postgres instances was 16K compared to 1.7K on EBS. Update latency on NVMe was 4 milliseconds versus 37 milliseconds on EBS. In the 5-minute benchmark, NVMe completed 19 million transactions, while EBS completed around 2 million of them. Now, let's take a closer look at what is happening under the hood and why NVMe setup is so much faster than EBS. So this is the interesting part. So this table, this presentation, this slide captures, where the 37 milliseconds is going with EBS. On the left-hand side, you have pgstat activity samples. And if you see with NVMe, there were 9 backends on IO data file read, whereas with EBS, there were around 29 backends. So 45% of the backends with EBS were actually throttled on data file read and IO, right? Whereas with NVMe, that was around 14%. The graph on right-hand side actually shows where the 37 millisecond latency with EBS is going. The red segment is page reads, and with NVMe, it was around 0.3 milliseconds, whereas with EBS, it was 19 milliseconds, right? And page reads are nothing but disk access again, right? The yellow segment, which is wall fsync at commit, NVMe was at 1.5 milliseconds, whereas EBS was 11 milliseconds, right? And wall fsync is also IO and disk, right? Because you are basically writing the transaction to the disk, you're backing it up, right? And the gray segment is lock and scheduler overhead. With NVMe, it was 0.2 milliseconds, whereas with EBS, it was 5 milliseconds. So as you see, the red and yellow segments were the places where there was most of the bottleneck, and it was all IO bound. This is a very interesting graph. So what this does is it is a Parka differential profile comparing CPU time spent between NVMe and EBS, right? So let me explain this. So when I saw this, it was very counterintuitive for me. So the blue dot is NVMe, right? And the red dot is EBS, right? And the y-axis captures various internal Postgres functions in the update path, right? And the x-axis captures the CPU share, right? And if you observe that most of the times the red dot is ahead of the blue dot, which indicates that the CPU share on EBS is much higher than NVMe. So this was counterintuitive for me because I thought that NVMe should spend more time on CPU, and why am I seeing that EBS is spending that much time? But then when we look at the right hand side, it actually shows how much of the time was busy, right? And on NVMe, 2253 CPU seconds. That time was the time CPU was busy, right? And that contributed to around 9.4 B cores. Whereas with EBS, it was 251 CPU seconds, and that was just 1 V core, right? And this was in a window of 250 or 240 seconds, right? So if you observe, even though the Parka graph shows that EBS has higher CPU share, most of that CPU share was actually waiting on disk, right? So that was a very interesting like thing that we noticed, that like CPU was getting throttled on IO, right? It was just waiting, even though the share was higher, it was not doing work. Whereas with NVMe, it was continuously doing work, and which is why you saw that kind of like throughput, which is 9 times better. So what we did was we also ran this benchmark for other operations like vacuum and logical replication, right? And as I just have 25 minutes, I will not be able to present those, but I'll cover the results and we will publish a report about vacuum and logical replication as well. So if you see, update was around 9.2 times faster with NVMe backed Postgres. With vacuum, we generated 10 gigabyte bloat on a table, which is the pgbench accounts table, and then we ran the vacuum in very similar like environments, right? Like very similar conditions. And if you see, NVMe finished the vacuum in 366 seconds, whereas EBS took 964 seconds. So NVMe was 2.6 times faster than EBS, right? And also, if you see if you see the IO wait, NVMe was basically 3 seconds, so it was not waiting on IO at all. Whereas with EBS, it was over 300 seconds. We did a similar test with logical replication, where we created a replication slot with 10 gigabytes, and then we had clients which were consuming this logical replication slot, right? And NVMe showed a decoding throughput of 89 Mbps, and EBS showed around 52 Mbps. So NVMe was around 1.7 times faster than EBS, right? And the amount of time it took to drain the replication slot, right? With NVMe, it was around close to 2.5 minutes, whereas with EBS, it was like 4 to 4.5 minutes, right? And what I have seen, like running a Postgres application company for a couple of years, this has cumulative effects, right? Like, so if the slot grows from 10 gigabytes to 100 gigabytes, the time to consume the slot can exponentially grow, right? So this is the benefit of NVMe, where like it flushes the slot faster and your Postgres overall is much healthier. So in summary, if you observe, NVMe backed Postgres is much faster, not only with respect to your standard operations like update, selects, but also these auxiliary operations like vacuums, logical replication, checkpointing. And as you know, those are the ones that dictate the health of your Postgres database. Now let's get back to the question on can we actually have NVMe in production? Can we get NVMe level latency and enterprise grade durability? And the answer is yes. There are three building blocks for that. First is configuring high availability with up to 2 standbys. We'll double click on each of these building blocks very soon. Second, continuous wall archival to object storage to guarantee data durability. And third, these backups power various operations such as branching, point-in-time recovery, read replicas, scaling, and more. And as you know, these are table stakes and essential for any production Postgres environment. So let's double click each of these building blocks. First, you can achieve high availability using Postgres streaming replication. You can configure up to 2 standby nodes through quorum-based replication, and this was added more recently in the past, 3-4 years ago, right, in Postgres. And this ensures that transaction is committed once acknowledged by at least one standby, right? So that reduces the performance. The quorum-based replication, with that, the transaction can go to just one standby. It need not get committed in both the standbys, right? So that improves like performance. And these 2 standby nodes can be spread across availability zones, making Postgres resilient to AZ failures. And you can configure failover when the primary, automatic failover when the primary goes down. And for this, you can use popular and battle tested open source tools like Rep Manager, right? Or you can build your own state machine to take care of all of that. You can also change this setup from 2 standbys to a single standby based on the criticality of the use case, right? And you still get availability, right? So if your use case is more tier 0, tier 1, say you're a bank, right? it's better to have like two standbys spread across availability zones. Whereas if you are like a tier 2, tier 3 application still in production, you could use a single standby, and that should be totally fine with, and you can configure it with synchronous replication or async replication based on your use case. Now, second building block is continuous wall archival and continuous backups to object storage for data durability. And you can do this with open source tools like Volg, Barman, or PG Backrest. They support performing full backups periodically and continuous wall archival to object storage like S3. And as you know, S3 provides like great durability of 11 nines, and this ensures that your data is never lost. With this approach, you can achieve as low as few seconds of RPOs, and you can recover the Postgres database at any point in time until your backup retention. And also these backups could be in across regions, could be replicated across regions to make sure that your Postgres is durable in case a region goes down, right? And one thing I'll say is that all of this orchestration of taking full backups, archiving the wall to S3, replaying the wall from S3 is already like supported in these open source tools like Volg, Barman, PG, Backrest. So it's not like very difficult to set them up. There is some work, but it is absolutely possible. The third is that these backups power various operations like branches, PITR, scale up, scale down, DR, right? So with branches, you can bring up isolated environment, which is a copy of your production in i- i- at a given point in time. And then you can use that for like dev and staging environments, similar with point in time recovery. And then scale up and scale down where, you can bring a new node from these like backups in S3, and then you do a failover, right? So that is also possible. Read replicas are very similar, where you can have a read replica which is actually uh, 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 being catching up from the primary, catching up with the primary from the backups, right? So that way you're not putting any kind of load on the primary. It's all wall replay from the backup, right? So it's minimizing load on your primary as well, right? So this backup is the heart of this entire production Postgres environment, because that powers all these features like branches, read replicas, scale up, scale down, point in time recovery, and more. And by the way, this architecture that I talked about, is already used in large enterprises like Datadog and Instacart, and they run their mission critical workloads on Postgres, which is backed by NVMe storage, right? So they get the best of both worlds. They get like solid performance because of NVMe storage, but then because of all the architecture that I talked about, it's enterprise grade. So they get high availability, durability, all the features that I talked about. So, to summarize, here are the two main takeaways from this talk. First is Postgres on NVMe storage can do more with less. We showed that Postgres on NVMe is much faster than Postgres on EBS for not only standard operations like reads, writes, CRUD operations, but also for auxiliary operations like vacuums, checkpoints, logical replication. Second is you can actually have this kind of a setup, which is Postgres backed by NVMe's in a fully enterprise ready manner. But you need to go through the right setup using tools like, Rep Manager for HA, Volg for backups and to S3, and then using that for like various operations like Pitter, branching, read replica, scale up, scale down. So in summary, this way you can get like you can have Postgres to do more with less, but also make it very reliable. So with that, I would like to introduce you to something that we recently launched, which is Postgres managed by ClickHouse. This is a native Postgres service that is uh, that is a part of our platform, which is ClickHouse Cloud, right? It uses NVMe storage under the cover, so it's very fast. So you get all the benefits of performance that we talked about, right? But it also orchestrates all the things we discussed about HA, backups, all these operations, right? It orchestrates all of that. So it comes with HA out of the box. You have continuous wall archival that's happening in the back end. It supports features like branches, point in time recovery, read replicas, PG bouncer, query insights, right? Like it supports all those features. The idea is you get like, very fast and highly scalable enterprise ready Postgres. And then one of the very big differentiation compared to other managed services is that this NVMe backed Postgres is natively integrated with ClickHouse. So within few clicks, you can start syncing your data from Postgres to ClickHouse, and we support native CDC capabilities with PeerDB, right? That's the company that like I founded, and it's battle tested across like thousands of customers, right? So within few clicks, you can have your Postgres transactional data in ClickHouse and make it analytics ready, right? And then it also comes with a unified query layer using the PG ClickHouse extension that you're seeing on the screen. So that extension enables you to query ClickHouse from the Postgres interface. So the idea is you're doing both transactions and analytics from the same interface. So it will minimize your application changes, right, to adopt ClickHouse. So TLDR, with these integration capabilities, within like few minutes, you can offload your analytics to ClickHouse and continue running Postgres for transactions. So you're getting best of breed, right? So enterprise grade NVMe backed Postgres for transactions, and ClickHouse for blazing fast analytics. So that's it from my end. Thank you. Very excited to be here again, and I would love to take any questions that you have. Bye bye.